Nowadays, our phones are capable of receiving information. If we take advantage of the sensors that our phone has pre-installed, we're capable of knowing the acceleration of a projectile in a parabolic shot. Our objective is to compare and contrast the real range of a slingshot and the numerical simulation.
No, Changui, ingenieros mexicanos, por favor. ¿Cuánto va? Son 1, 3, 6, 9. Son 3, 6, 9, 12, 15 metros. No sé, aquí cuánto fueron. Fueron 15. 15.30 metros. Le estás poniendo como 20 centímetros adelante. La más que llegado es casi a la de 15. ¿Seguro? ¿Eso es la de la...
Well, this is going to be our theory and data. Alright, for the slingshot, we know that to calculate the acceleration and the initial velocity of the phone, we first need to know where the formula of final velocity equals the square root of 2 times the acceleration of the distance comes from. Alright, so it comes from the formula of work equals to the final kinetic movement and the initial kinetic movement. Work is equals to 1/2 of the mass times the final velocity squared, and as you can see, this one is cancelled because it's equal to 0. Work is also equal to force times the distance, so this will be equal to 1/2 of the mass times the final velocity squared, and we know that force is equal to mass times acceleration. So in this formula we can cancel mass, and this leaves us with 1/2 times the final velocity squared, and we can say that the final velocity squared is equal to 2 times the acceleration times the distance, and the final formula would be final velocity equals the square root of 2 times the acceleration plus times the distance. Now our data. Our data is okay. We did 10 tries. We threw the phone 10 times at different angles. We threw it 2 times at an angle of 45 degrees and 8 times at an angle of 30 degrees. We obtained different ranges, if you can see. We obtained different accelerations with this formula. With this formula of acceleration equals the square root of the acceleration component in x squared plus the acceleration component in y squared plus the acceleration component in z squared. Now, the final velocity, we obtained it with the formula, as I already said, equals to the square root of 2 times the acceleration and the distance. We obtained its components in x and their components in y. We also obtained its flight time, and now our results are going to be these ones as obtained. We can say that our acceleration tends to be a little different. It isn't a straight line, because obviously in our measurements it was impossible for all of them to be equal. You could say the same for the initial velocity, because since the acceleration changes, also the initial velocity changes. Also, you can see that this graph and this graph are exactly the same, just a little, well, the initial velocity is just a little up in the y-axis. Okay, now the flight time. We can see that the flight time depends from the acceleration and the initial velocity. So because of the acceleration and the initial velocity are not in a straight line, we couldn't get a flight time in a straight line because all the data was different. Now, as for the analytics, we can say that calculated with procedures and all that, we can see that the initial velocity in y it's a little different, and as for the initial velocity in x, we can see that it turns to be similar to completely different from the velocity in y. Now, comparing, we can see that the initial velocity versus the acceleration, you can see how this changes completely. Okay, we can say from this one that the initial velocity it's greater than the acceleration. Also, that if you can compare these both graphs, you could see that they are almost the same in their shapes, which means that the initial velocity and the acceleration should be pretty similar. Okay, now the initial velocity in y compared with the initial velocity in x. We can see that this chart has a very strange behavior, because we can see that the initial velocity in the x component will always be the same for one of the throwings. So you can say that, as it's pictured in here, the initial velocity in the x component will always go in this one. It will not change in perfect conditions. Instead of the initial velocity, in the y component, it will change. For example, in here, in this part of the graph, it will decrease, and in this part it will grow a little until the object falls. Now, my recommendations for this project will be: learn how to use the formulas, especially these ones, because once you get a hold of how to using them, you will spare a lot of time in mistakes. It is also very helpful to know where this formula comes from, so it's good to know that it comes from the work formula. And also it's very good to consider that the acceleration, you should take it in the three components: x, y, and z, because if you take it in only these two components, it wouldn't be a 3D object. Well, also for the range of every throw, in the analytics way, we determined that the math just didn't add up, because we got an extremely big range in some of our results, and in some of them we got really accurate ones, like in this example. But in this one you can see that it's not very accurate, so I don't know, I don't think it's really accurate.
A la primera salió, ¿no? Nomás que llegamos casi a la de 15. ¿Seguro? ¿Esos son los de la...
As for our conclusions, we can say that we're going to get our objective because we proposed to prove that the analytic method is different from the experimental method. So as you can see in these ones, in the range, as for the range in the analytic part, it's different from the range in the experimental part. So you can say that the accurate way to get the range of a parabolic throw, it's the analytic way more than the experimental way. Also, all the comparisons that there are between the initial velocity in x and the initial velocity in y, and I would say that that's all.